I started recording after this introduction. Okay, so this is what flow, because you must know the flow how we are going to do in this course. Right? Regression experiment approach are discussed through that video, right? And the order what we are going to cover in this course is like this, right? That followed by probabilistic approach, then we go for the support vector machine, then artificial neural network, backpropagation algorithm, then we concentrate on these generating models, combination model, example Gaussian mixture model, and then sequential model, hidden Markov model, and then followed deep learning techniques. This is the flow what we are going to follow. We thoroughly discussed about this linear regression, and then now we phase of a linear model for classification. In that we are actually in the discriminant approach. So I made you clear of this course what right so far and what we are going to do in that coming classes, right? So today, right, it is the revisit of linear model for classification. I hope you have seen all the videos related to this. I mean, I have posted 3 videos related to it. So I hope you have seen all the 3 videos. It is compulsory. It is compulsory to see that, and I asked the representative to take the attendance also, right? So now in this linear model for classification, there is one topic what is called the dimensionality reduction technique. Dimensional reduction technique, right? So what does it mean? In that we are trying to find out the transformation, right? See, for example, that original data, if it is of size m cross n, we need a matrix n cross m, right? W matrix m cross n, W transpose is n cross m, and we get this vector y, right? So they are interrelated like this, using this matrix with n. So what we call this as a dimension technique, right? So we do this objective what we have it in our mind, right? Basically this is needed to reduce for the classification using this discriminant approach like SVM, and even going for probabilistic approach, right? We need to do of reduction because the data sometimes, if it is large, the number of features like image data and all, right? One way is actually collect the features from the data. If we know, right, what info needed from that data, we will infer from that by collecting information out of it. But this we are discussing here is the statistical approach. We are not going to have an expertise on the data. We do this just to statistical analysis of the elements, the whatever the vectors you are collecting. So in that we are having important techniques. Still we have other techniques available, right? Like ICA and right, but we are going to discuss one of, right? So like PCA component analysis, and we have linear discriminant analysis, and this one is the kernel linear discriminant analysis, and this is what we call as independent component analysis, right? Principal component analysis, linear discriminant analysis, and this linear discriminant analysis, and then we have independent component analysis, right? So in all the cases our objective is to get matrix, this matrix W, right? So which is basically of size m cross n and transpose of size n cross m, right? We are interested in getting this W that does some after doing this dimensionality reduction. For PCA, in case of PCA, what we do is, suppose that if you are given a data like x1, x3 and so on, and right, so we know that individual size is going to be m cross 1, right? So this is that m cross 1, and you have n data available in the data set, right? So what you are going to do is going to compute the estimate of the covariance matrix. In pattern recognition, we say that it is a scatter matrix. Yes, scatter matrix. The estimate is what here, right? So the covariance matrix is the statistical definition, right? We know that it is the basic definition of the covariance matrix is like this: expectation of xs transpose minus mu x transpose. This is the actual definition for the covariance matrix, where this x is a vector. It is a random vector. X is basically the random vector, right? And these things are considered as the outcome of it. These things are the considered as the outcome. These are all the training data given to you. These are all we are considering it as the outcome of random vector x, right? But what we do is we will not actually go for this expectation, because expectation needs, see, we know that by definition expectation of x is basically x into the density function is involved dx, and then is minus infinity plus infinity. So this is the way how we have to compute the expectation, right? So that involves the density function. That is the most important thing, right? Available. So we are going for the estimate the covariance matrix, estimate of 2 in pattern recognition terminology, we call that as a scatter matrix. What we do is, from the data itself, we will do this estimation, like x1 is a column vector x1 transpose plus x2 transpose, like that. We have xn transpose. There are n data available, and then you are going to take this average. This is the first part of it. Part 1, we can say that yes, part 1, right? Then we compute this mu x. When you do this computation, end up with the size. Sorry, the size is going to be your cross m. Sorry, because the size of x1 is, and it's, and if I do this multiplication, it will end up with m as you see here, right? How we estimate this? I'm talking these things as the estimate, right? So that is very important. So we can say that it is, right? So say that m mean estimated thing, right? So this one we do it like x1 plus x and so on, the average 1 by n, and that is what is m. M cross 1. Then what we do is m transpose, right? So that the size actually become, let me put it as a capital M. So that is going to have the size of right. So this one we call it as S part 2, right? Well, we compute S as S part 1 minus S part 2. So this is basically the estimate. So given at data for doing this dimensional, we need to do this one for the testing also. right? So to find out this estimate of this matrix here, once we compute this matrix, we go for finding out these eigenvectors. The eigenvectors of this we computed, right? We compute eigenvectors of the eigenvectors we need to compute. So vectors of S finding you see that S is the matrix and your EI is eigenvector, right? So the we have this EI is eigenvector, right? So the vector that satisfies this expression like this is what we call it as this eigenvector, right? So we compute this eigenvector and we collect it, right? So we have this E1, E2, and so on. We get actually En eigenvectors, and we have that corresponding also available. So that is lambda 1, lambda 2, and so on up to this lambda n. Like this. And then let us assume that you have collected in such a way that the eigenvalues are arranged in the order. So that means that lambda 1 greater than lambda 2, it goes like that, and n, right? The interesting point, I will write that expression here. So y is b transpose x, and took this as m cross 1 and this one as n cross 1 and going to be your n cross m, right? So what you, yeah, you get, yeah, yes, right. Thank you. You're right. So you actually get I vector because the scatter matrix going to be your m cross m, right? You get m eigenvectors, right? You're right. And you get this m eigenvalues, right? Lambda 1, lambda 2, and so on up to this lambda m. And what is more important here to be communicated is if I plot these lambdas, right? So that is the important to be noted here, right? If I plotted this lambdas, let us say that I'm not plotting in a discrete, okay, let me plot it in a discrete form. So it is like this. So if I'm just having this in decreasing order, and what you see here is after, this corresponds to lambda 1, this corresponds to this lambda 2. These are all the eigenvalues I'm talking about, right? So let us say this is going to be a lambda m. Just 13 values, 13 or 14 values. This is not hard and fast number, right? But in practice, in image processing and all, this number is most popular. I mean, this normally ends up with this 13, around 13, right? So that's what I am talking about this number. But this will vary, depends upon the data. What thing, right? You have to apply, of course, this threshold, right? The top eigenvalues. The main important point to take down is the values reduce after a finite number of values, So in fact, for example, in m value for that image processing for a small image 50 cross 50, if the size is 2500 cross 1, means you are going to have 2500 eigenvalues, right? In that, only 13 values are significant. 13 values are significant out of 2500. The thing to be noted, and we are going to collect this in, let me take so n of values, right? And then the corresponding eigenvectors, right? So you are going to form a matrix, right? So you know that the eigenvector size is going to be m cross 1, right? So you are going to arrange them in row wise. The W transpose size n cross m. So let me put it as, E1 column wise we will arrange, right? E1, E2, and so you have this n here. So remember that there are the vectors. So it is a vectors, you are arranging them in a column form. Each column is going to have the size of m cross 1. So and hence this W is size is m cross n, because you are having n columns in it, right? So m cross n. The reason W transpose is becoming right. So this is actually used for getting this dimensionality reduction, right? So the additional points what you must know is the scatter matrix, of the data. So let me put the scatter matrix associated with the variable x. You know how to compute the scatter matrix. Earlier I used the term this one with subscript x, indicating that it is a scatter matrix associated with the random vector x here, right? So we are having a very good relationship between this and your sx is basically transpose sxw. This is a relationship, the scatter matrix, the covariance matrix relationship, right? Basically this is what we get from so this is we can prove that statistically cy is w transpose cxw, right? Okay, this is important. And another interesting observation is the covariance matrix cy, what we get here, it is going to be diagonal. It is very important to note down this, actually this point, right? See that the covariance matrix of the projected data what we get is diagonal. It means that after project, so we have these elements, after projection we have n elements in it. What we really achieved, so yeah, someone is that clear, or what is that? There are m eigenvectors, that's fine, okay, but we take the log, right, to map to redemption. Yes, you are right. Shankaran. Okay, so now PCA is we make y1 to this yn, right? So they are uncorrelated. This is and you have to be careful. Independent is different, uncorrelated is different, right? So there is another dimensional reduction technique. Make them independent. It is what we call independent component analysis. PCA makes only uncorrelated. ICA actually makes the data independent. It's one step ahead, right? So we need to do this PCA, and then we will try to make them as independent. That is independent component analysis. Anyhow, we will discuss a few also, right? So now, as far as this PCA is considered, we are making the data uncorrelated, right? That is the another important point to note on. For example, we can say that, suppose that I'll just give you one example of understanding this, right? So doing, yeah, like this, right? These days with reference to this x and y coordinate, right? So in other words, these data are represented these vectors are represented. This is the basis function, right? So you know that 2D basis function, 2D basis function, no? A standard, we can say that it is 1 0 and then 0 1. Basis function is the minimal spanning set. We can say that it is a minimal spans that complete 2D. The spanning set, minimal spanning set, no, in that case they should be what, independent automatically, but in the special case it is also becoming what, orthogonal also, right? So what does it mean? It means that any arbitrary vector, right? So if I choose this as a vector, so let us say these elements are x and y or x1 y1, right? So this can be represented as x1 into 1 0 plus x2 into 0 1. It is like that, right? So any vector in that space with this basis function, right, we are able to represent as the linear combination of this basis vector 1 0 and 0 1, and that's what we call it as this basis of this right? But now what is that PCA is going to do? PCA actually is identify the direction of the maximum variance. So this is the direction of maximum variance. It means that after projection, I'm talking about, right? After, right? It means that we can PCA as feeding the data, right? With reference to basis, we can say. Originally, the bases are 1 0 and 0 1 by default. Now you are going to represent the data with reference to what? The eigenbasis. So that eigenvector E1, vector E2, right? So this is what I am doing. What does it mean? It means that the vector, right? Whatever we had, we are now trying to represent with respect to E1 and E2 instead of representing with respect to what? 1 0 and 0 1, right? So let us say that, so this is the, right? Let me draw it again. And your eigenvector is in this direction, right? So let me have the data like this, right? So with reference to the original basis function, if I want to know about what really you are doing, you are projecting the vector, perpendicular projection you are doing on this basis function like this. If I do that, you will get a coordinates. This is going to be your x1 and this is going to be your y1. For example, let me take this example, right? So that will be better. This vector we will consider. So going to be your x1 here, and then if I project here, get this as a y1. So with reference to this standard basis 1 0 and 0 1, so we are in this coordinate as x1 and y1, but same data now I am trying to project on, right? So we have is now they are perpendicular together, and these are all the eigenvectors. This is E1 and this is going to be your E2, right? So project this vector to this basis E1 here, and then I'm going to do this projection E2. It is going to be like this, right? So you get some other value. Let us say that this is going to be your P1 and this is going to be your Q1, right? The same vector now it is being represented using this P1 and Q1. So there is a happening now, right? So these two actually converted to P1 and Q1. That is what the transformation is doing. And remember that in this transformation, the number of elements are not changing. This is 2 cross 1. This is also 2 cross 1. I'm not going to change it. But when you observe the value of Q1, that is the most interesting point, right? So as far as this data is considered, whatever the vector eigenvector, so those things are bounded, right? Those things are bounded between, no, so it is like that within this small range. As to say here is the value, right? They are going large. What I really mean by that is, so this between say, 0.1 to 0.1, and when I say this Q1, see, let me write, this is just the example only. Q1, I'm saying that it is ranging from minus 0.1 to plus 0.1, and then P1, let us is right. See, even I didn't have a data in this direction, but still in more general case, right? So it can go, for example, minus 10 to plus 10, say, for example, right? So compared to this Q, the range of P1 is actually going to be that large. In that case, even if you ignore the data, I mean Q1, it is not the big loss. That is the thing. That is the thing. It means that it is a lossless transformation only. There is no doubt in it. But that loss is very insignificant because, right, property of this PCA, right? So that I can just make use of this P1 alone, right, to represent the data. So that is the meaning of it. My in the original data, original basis, I do like that, right? So instead of getting this original value, what the projection is minus 0.01 to plus 0.01, let us consider like that. It is very less. That is what I'm trying to say, right? So these values are too little, that range, right? So instead of putting that original projected values between this range with 0, that will not, right? So that is what exactly we are doing. This is what we call as the data representation with the less number of elements, and hence further we can use it comfortably for the classification. Either it is a SVM or nearest mean or nearest neighbor, right? So we have a different classifiers. We are going in the coming class, but I'm just saying that nearest mean, and then we have nearest. So in that case, after projection, we will give us an input to this, and we can do this classification, right? So this dimensionality reduction, right, helps in having a good packing capacity without losing that information more. That is the important point to get down. So it is used to store the data also, like image compression, right? So, and data representation for classification, right? So this is what is PCA, but the only drawback of this PCA is it does class label, right? So whatever the data available, right, it is not to be used completely for finding out these eigenvectors. So this doesn't use information, right? So that is a drawback of this PCA. So there is another method to project is what we call LDA, linear discriminant analysis. In that case, that data, we will represent it with double subscript and so on up to what? xn1, and then we have x21, x22, and so on up to this x, right? Right, let me consider one x3 and so on up to this xn, like this, right? So now the data, of course, the total number of data are going to be n1 plus n2 plus n3. We have this number of data available. This is the training data what is given to you, right? So now what we do is, in this case, instead of computing one scatter matrix, what we did in PCA, here we have what is called two scatter matrix. One is SB, which is called between class scatter matrix. And then we have what is called within class scatter matrix. So this is actually the estimate of the expectation, right? So it is like, what we do is, say for example, these data are arranged like this at particular dimension. I mean feature dimension, we can say. So let us say that in this case, one illustration is done using, so it is like that, class available, right? So we have two objectives, in this. After doing this projection, to that dimension, we have two objectives. One is, after projection, you would like to make the vectors within the class, this class, these vectors, this needs to come closer to each other. So after all, see, this is 2D. So only choice after doing this projection is going to be 1D. So let me plot that. After 1D, this 1D means I can draw it only on the straight line, right? Because that is the way you can do here, right? Because it is 2D what I have considered. So after projection, our goal is, we wanted this vector to be closer within the class. It should be so close, right? Like this, it should be so close, right? And this is one objective. We wanted this vector within the class to be close to each other. And then we wanted this separation between these two, the class, that should be maximized, right? Between the class, the separation should be separated, that should be very large. You wanted this to be very large, and then you wanted this vectors to be closer. We wanted this two objectives to be satisfied after doing this projection. After doing this projection, you want to do that. Why we need to do that? We can, if we have a good separation, then the classification will be easier, because particularly, for example, in case of support vector machine, we are interested in finding out the line that divides these two class, right? So in that case, we are if the separation between this two classes is large, then finding out the line will be easier to us, right? So this actually favors the classification rate, right? The deduction rate. So that is the goal, right? So to do that, what we do is, we have two scatter matrix. One is SB, between class scatter matrix, and then another one is the within class scatter matrix, which measures that. Between class scatter matrix measures how far the centroids of various class, right? So that is going to be well separated, right? So to do this task, what we have to do is, we compute this SB estimate. I'm talking about this estimate, right? So what we do is, first job is to find out the centroid estimate, right? The C1 centroid is 1 by N1. Then we have to do this average. So it is basically that mean for the class 1, mean vector of this class 1 estimated. And similarly, we can do this 1 by n2, we have this x21 plus x22 and so on up to this x2 n2. So this is going to be C2 here, and then we have C3, which is 1 by n3, right? So we have this x31 plus x32 and so on up to this x3 n3, like that, right? So we compute the overall centroid also, which is C, which is given as 1 3 C1 plus C2 plus C3. So then what we do is SB is basically we compute this scatter matrix individually for this class 1, class 2 and class 3, and we do the simply the summation. So in this case we have 3 class 1 to 3, right? So we simply compute this S1, S2, S3, right? And we do this summation, right? But if we have different number of elements, right, in each class, then we will make use of that also for doing this linear, right? So it is like NR, right? And we do a proper scale, right? Scaling is done, and that is finally end up with what is called this between class scatter matrix. Within class scatter matrix is the scatter matrix computed for the centroids what we already computed. Using this C1, C2, C3, we do scatter matrix. It is like 1 by 3, right? C1 minus C. This is like exactly what we did in the previous PCA problem, plus C2 minus C into C2 minus C the whole transpose, plus C3 minus C into C3 minus C the whole transpose. And there are varieties, actually the variations available for computing this between class scatter matrix, right? So based on that normalization, based on that scaling, there are many variations, we can say, that proposed in that literature, right? And in this course, of course, we will fix the between class scatter matrix like this only, SB, and then for SW within class scatter matrix. What is more important is the trace. Even in case of PCA, it is true, but I'm just saying that the trace of SW will give you the information about how far the vectors are closer to each other. And similarly, the trace means summation of the diagonal elements, right? So the trace of SB will give you information about how far the centroids of, the vectors within the, okay, here, I'm sorry, I think I did a do small correction here. This is going to be your SW, this is within class, how far the vectors are closer to each other, and this is going to be the between class, SB, right? So it's like that. So the trace of SW will give you how far the vectors are closer to each other within the class, and trace of SB will give you how far the vectors, the centroids of various classes are well separated, right? So after computing this, we go for computing the eigenvectors corresponding to SW inverse SB, right? So in fact, as usual, the eigenvectors means this into V is equal to lambda into V. In fact, we will write this one in a different form. SWV is lambda times SWV. This is a better way of writing rather than writing in this way, right? So because SW, after computing that, there may be chance that it is not invertible also. So that is a important problem in actually LDA. finding out this inverse, right? So it is comfortable to write like this: SBV is equal to lambda SBV here. So as usual, we put the subscript here to indicate that it is the eigenvector corresponding to the eigenvalue lambda I. And as usual, you are going to arrange them, the eigenvalues in a decreasing order, and you get m eigenvalues, and then you are having a corresponding eigenvectors. The same procedure like the PCA what we had, right? So this is that eigenvector E1 and so on up to M, right? So we select only the n eigen values, the largest n eigenvalues, and then we form a matrix W with those eigenvalues E1, E2, and so on up to this En, and then we use this one for the dimensionality reduction, right? So this is about this LDA. So this helps in bringing the vectors after projection within the class closer to each other and centroids of various classes to get well separated after projection, and that's what this LDA is, right? So suppose that if I have a data of this form, so one data is like this, and the another data is like this. You see that? So this is the way how we are having the data, right? If I apply this raw LDA also, with this objective, after projection, we cannot expect after projection, right? So after performing PCA fails here, even after using this LDA, so you will not get a very good separation in 2D, right? So this is basically what I am telling here is the projection from 2D to 1D. This is 2D and this is 1D here. And in this case, what will happen is the vectors gets overlapped after projection. You will not get a very good separation, right? So like this. And that is a reason what, we go for what is called KLDA. This is very popular and very important trick, just like what we use this kernel trick in regression. This is the kernel linear discriminant analysis. Kernel linear discriminant analysis. So in this case, what we really do is we do the task of this LDA after projecting the vectors to the higher dimension, right? I think I told this one during the regression problem, the kernel trick using the regression problem, right? Say for example, this is 2D, right? So if I project the vector, for instance, what is given in the blue color, right? So let us say that you project or you make that vector to come out of the screen, right? So in 3D, what I'm trying to say here is, and you have this circle here, and talking about this 3D view, right? And then right, you are making this to come out, right? You can say that this is the plane in this direction, and you can imagine that these vectors are available on this plane. I hope what I'm trying to say, this is the original XY. Now you are introducing what is called Z, right? So this is the plane, right, parallel to this, the plane XY, which is coming out of the screen. You can imagine like that. So whatever is there on the screen, on the laptop, whatever you see here, let us say that the cross are coming out of the screen, right? So you get a separation. So it is like, whatever the element you have, XY, you introduce what is called, if it is a class 1, you introduce what is called 1 here, and if it is a class 2, you introduce that it is 2 here. I mean, this is the I'm just saying this idea only, but we are going to do this exact work how we are able to do this one in KLDA, right, in the coming class. So when I do that, and this may be 0 also, right? So on that same plane, and we can have some separation on the Z plane, right? So that what will happen is we get a good separation between this. What I'm trying to say here is, if I project the vector to the higher dimension, we get good separation, right? So we need to project to the higher dimension for good separation, but at the same time, we need the data to be well packed, right? So for that, we need to do this projection to that lower dimension. So both are needed. We need to map to the higher dimension and then bring back to the lower dimension. That is the best way, right? So that is what it is done using this KLDA, right? But what is more important in that is without really mapping the vector to the higher dimension, really mapping is the thing that we'll see how we are going to do, really mapping the vectors explicitly to the higher dimension. Just like what we did in regression, we call it as a kernel trick. I'm repeating once again now, the kernel trick is used in many places in kernel LDA, and we are going to use this trick in SVM also. This is very important, that kernel trick. We are going to discuss this KLD in the next class. That is our question here. By mapping into higher dimension, we do not create any additional information. How can we separate data into classes in the higher dimension? Also, mapping into the higher dimension will be very dependent on the functions we use to map. The point is, see, you can actually view the data as, let me read the name who asked this question. Shiva Shankaran, right? So are you from EC or the other one? Shiva Shankaran? Okay. So the point is, we are viewing the data as a representation on the space. 2D means plane, and 3D we know. Then the higher dimension is hyperplane, hyper space, right? Right, where we look for this hyperplane, right? So basically, we view the data in the as a representation of the data in that space, right? So now, for example, in case of discriminant analysis, what we really look for is the good separation between the vectors. That is the thing. Why we need good separation? We need good separation because I can find out the line that divides, right, this cross and circles. Suppose that if I have something like that, then I can find out that line that divides this into two. Then this will help me to find out the index if I have a new vector coming into picture, say, right? If it is in this direction, I can say this is of class 1, and if this vector is in this direction, we can say that it is a class 2, right? So we need to find out this line that separates these two vectors. So if I have a very good separation between these two after doing these projections and all, right? So then we'll be happy. That is what the thing, right? So we try to represent this data in the way that after doing this projection, we wanted this to have a good separation between these two, right? So one way, for example, in this case, we represent this data, right, by doing some manipulation, like, you project the vectors, whatever is there in that inside here, this which is given this blue color, to come out of the screen, right? Let these red circles be on the screen itself, like on your computer screen, and this blue crosses, right? So let it come out of the screen. Then you see that you have a good separation between these two, and I can find out the plane which divides the circle and the cross. You got my point, right? So that is the thing. This is the intuition what I'm trying to say. But in general, right, if I map the vector to the higher dimension, not only by this way, right, some other manipulation also you can do. If I do so, if I map the vectors to the higher dimension, what we really achieve is a good separation in that space. So that is the thing. But what functions to be used, and what is it dimension change, right? How much I have to map to the higher dimension? They're all the tricky thing, right? So that is what the basis function, just like what we used in regression problem, that m in that it is m basis, right? So depends upon that, you know. So it's a tricky thing. But what is more interesting to be communicated is, right, we do this using the kernel trick. We don't really map this one to the higher dimension. We have a trick as if, you know, it is doing the job in the higher dimension, right? So it is like we do this linear discriminant analysis in the higher dimension without really mapping the vectors to the higher dimension explicitly. And that is what this kernel LDA is going to do, that we are going to discuss in the coming class, right? So we'll stop here. We'll continue the KLDA in the next class. Okay.